All right, we're going to probably embark on one of the most difficult lessons that we've got to learn as 8th grade students, and that's how to solve systems of equations algebraically. And we're going to start with trying to use elimination. It's the easier way to solve systems of equations when we can't graph them. We've got to do it algebraically. We've got to give an algebraic solution. What we're really trying to do is we're trying to find that one point at which our two lines intersect. So you can see that I've drawn two lines over here, and what I'm going to do is, I don't know why my pen's acting up, but what we're trying to do is we're trying to find this point at which our lines intersect and share space, share a point between the two. And so we're going to have some sort of x value, some sort of y value. Well, there's a lot of different pieces that go into making sure you understand how to solve systems of equations algebraically and using elimination. And so the first thing I'm going to ask you is, do you know how to, and we're going to go through a list of things if you know how to do them or not. And then what we'll do is we'll be able to put them all together to see if we can solve a system. My first one is, do you know how to find perfect opposites? Do you even know what a perfect opposite is? The way that we're going to see it is we're going to see possibly something like 3x and negative 3x. Those are considered perfect opposites. You may see something like negative 9y and positive 9y. Those are perfect opposites, and what we have to realize with perfect opposites is that they will combine to cancel each other out. They will combine and form 0. Okay, so basically they're canceling each other out. So that's the first one that you have to know how to do, how to find perfect opposites. All right, so here's an example of a system of equations that we would take a look at. And do you see perfect opposites anywhere? Well, I do. I see them right here with the x's, negative 9x and positive 9x. And what we usually do in class is we put a box around them, and then we're going to go ahead and cross them out because those would eliminate. So that's really what I'm going to ask you to do is, can you find perfect opposites? And then later on in some of the examples, I'm going to ask, are you able to create perfect opposites? Because the more difficult these become, we've got to actually go ahead and create our own perfect opposites. But being able to identify them, that's the first step. Okay, so what's next? Do you know how to combine like terms? Let's take a look at some terms that we could combine and see if you're able to do it. If I was able to present negative 3x and 2x to you, would you be able to combine those together? And what we've really got to do is we've got to look and see that we've got 3 negative x's and 2 positive x's. And I like to say that we match them up, or understand that negatives and positives cancel each other out, and we got to understand how many are left over. Well, I've got more negatives than positives, and so I have one extra negative than positive, so combining them would give us negative 1x. What if I was to give you positive 8y and negative 2y? Well, we do have more positives than we do negatives. When we cancel those out, how many more positives are we going to have? We're going to have 6 more positive y's than negative y's. And so that's combining y's in that case, and we can also do it with just integers. If we had negative 17 and positive 14, I've again got more negatives than positives, and so I have 3 extra negatives than I do positive numbers. If you're able to combine like terms, that would be number 2 on our list of things that we have to be able to do. Okay, so let's go back to our example here. If I zoom in and take a look at this, we've already crossed out our x's. I've got to go ahead and I've got to combine like terms. I want to combine my y's together. I've got 7 positives and 6 positive y's. That's going to give me 13 positive y's there. And I'm going to combine my numbers that I have. I've got a negative 2 and a positive 15. I've got more positives than negatives, and so that's going to give me positive 13 there. All right, if you can combine like terms, you're on the right page, and that's 2 steps down, 2 more to go. All right, step number 3, can you solve a one-step equation? The way that I teach equations to my students is almost like a ping pong match. We've got different terms. I've got negative 3x, which is multiplication. I've got my ping pong net here in the middle, and I've got a positive 18 on the other side of the table. And so one of the things that we hate to have is negative variables. I tell all of my students we do not want negative variables. So let's go ahead and hit that term over the net. And when we ping pong a term over the net, it changes to the opposite. So this was negative 3x. It now becomes positive 3x. Now our whole goal is to get the x's all by themselves on top of them being positive. Well, I've got them positive on the right side, but I have this positive 18 here. So let's go ahead and hit that ping pong ball or that term over the net. And now that's going to become the opposite of what it originally was, to negative 18. So now we're going to model what we have. I've got 18 negatives, and that 18 negatives is equal to 3 positive x's. If I'm going to model this correctly, I'm going to split my x's into 3 separate x's. Those x's are equal to 18 negatives, and those 18 negatives are going to now get split up evenly amongst the 3 x's. And so each x would be worth 6 negatives. And so we have our first piece of our point that we need, that x equals negative 6. Now where does that go? Well, that's going to go all the way back up into our answer at the beginning. Where's that point at which these two lines, these original lines, intersect? Well, that answer would go up here as the x value if we were solving a system right now. So that's what you need to know, a one-step equation. Are you able to solve a one-step equation, yes or no? If you are, you've got step 3 down, on to step 4. And the last step. The last step is the most difficult. We've got to be able to substitute in a value that we already have found, and then we've got to be able to solve it. Because what we're finding is the other value. When we have two value equations like x and y in an equation, we've got to be able to substitute in a number for one of them so that we can solve for that other letter, that other variable. So just like a coach would substitute a player into a game, we want to take one of these letters out of the equation and we want to substitute in a number. Well, I'm going to tell you right now that y is equal to 1 for this equation. So we're going to take our y value out of the game, and we're substituting the number 1 into the game for it. And what this is going to allow us to do, if we rewrite this, we've got 3 times x plus 1 equals 7. Okay. I've got 3 terms, 2 on one side of the equation and 1 on the other. I'm going to ping pong some of these terms back and forth and try to solve for x now. And that's going to give us the other piece that we need to our point of where our two lines would intersect. So I'm going to go ahead and I want to get, our goal is to get 3x by itself. So I'm going to send positive 1 over the net. And when I do that, that becomes negative 1. It changes to the opposite. So I've got 3 x's, and when I combine like terms here, I've got more positives than negatives. So I've got 6 more positives than I do negatives. I'm now going to go ahead and model this. I've got 3 x's, and those 3 x's are equal to the number 6. And if I split the number 6 up evenly amongst the x's, I'm going to be left with 2. So I get x equals 2. Substituting and solving is the last piece that you need to know. Alright, so this is all of the pieces. Take a look at one of my other videos on how to go ahead and solve one of these systems of equations algebraically. And if you can remember these 4 steps, you should have no problem finding this right here, the x value and y value, without having to graph a thing.